Hello, you're welcome back. All right, we are going to continue from where we stop. Okay, so now here in this video, we are going to be looking at leakage current in a transistor. Now, why is it called leakage current? Okay, already know when we treated our diode, we said that there exist minority charge carriers in a semiconductor. Okay, that can actually flow through the semiconductor with or without no electric field applied to that semiconductor. So such a minority carrier is independent of the input to that particular semiconductor. So now in the case of a transistor, you know very well that this is we have our output, okay, and we have our input. Now it's only when you apply your input, it's only when you supply a current to the transistor that it should give you an output current. Okay, but you discover that in some cases, even when you don't supply uh, an input, like in this case, I'm starting with a common base configuration. This is a common base circuit, right? So of course, you know very well that I've actually supplied the current by applying a voltage, okay, across the emitter and the base. Then of course I take my output across the collector and of course the collector and the base. Base is common. So now it is expected that it is only when I supply this emitter current, okay, then when this emitter current actually flows through the transistor that I will be able to have a collector current, okay, because we already know that the DC transfer, we call it DC transfer ratio, DC transfer ratio of the common base configuration, which we call alpha, okay, make us understand that the transfer ratio is going to be equal to IC all over IE, right? So, which simply means that for me to be able to get my collector current, so I have to multiply the transfer ratio times the emitter current, which is my input, okay? So which simply means that if it happens that there is no emitter current, there's a situation where I open the emitter, okay? I create an open circuit. Of course, you know what an open circuit. Once there's an open circuit, no current actually flows. So let's say I created an open circuit that will actually cause, that makes the emitter, okay, emitter current to be equal to zero. So if I should put zero into this particular expression, it's called that collector current should also be equal to zero. So I shouldn't expect to have any current, okay, flowing through the collector. But it happens that contrary to what we expect, okay, we still measure current flowing through the collector, okay, flowing through the output circuit. And the question is, what is that current? What is it called? All right. So that is a current that is called the leakage current. And that leakage current, you already know what it is from, is due to the minority charge carriers. Okay. So now, so there's bound to be a leakage current that is actually gotten, that is recorded at the output of a transistor, even when there's no input. So in this case, in this common base circuit, okay, such leakage current, I call it ICBO. Okay, why is it called ICBO? It is a current that is passing through, okay, current across or flowing through base collector, because base collector is my output, you know that already. The current flowing through base collector when the emitter, okay, when the base emitter is open. So current through collector base with an open emitter. Let me say that again, okay, or let me write it down. Current, please pardon me, current through, that is flowing through collector base. collector, okay, base with an opened emitter. Okay, so please take note of that. That is a leakage current. So that leakage current flows even when there is no emitter current. Okay, so you still record ICBO. Now, what if there is an emitter current, okay, connected? Then the leakage current still flows along with the output current. So invariably now, for a situation where I now have, okay, uh transfer, all right, when there is a transfer, when the transistor actually transfers current to the collector, okay, so that means the collector current now I'm going to have is going to be, you know what it is, okay, alpha IE, then plus the leakage current, which is of course is ICBO. Is it ICBO? Please pardon me. That is not. Is it ICBO? What is open? What is open is yeah, ICBO, right? Okay, ICBO. All right. So that is so. We simply means that my collector current is not just going to be the current that is transferred, the emitter current that was transferred, alpha IE. Okay, it also I'm going to add also ICBO, which of course is the leakage current that is obtainable at the output. So please take this as equation 1. Now, another thing you should also know, we know already, we know that without leakage current, okay, we meant to understand that transfer ratio is always um, the amount of the input that is transferred to the output, okay, and we now discover that if I measure the output current IC, all right, you have to measure the output current, then we now divide it by the input current, okay, IE. But it happened that the output current, all right, has some leakage. So that leakage is not a transfer. So I have to subtract it. I have to subtract it from the IC, okay? Because the leakage current is not part of my transfer ratio, because alpha is you call it DC transfer ratio. Why is it called DC transfer ratio? Is the ratio of the input that was transferred to the output. So since at the output I have a current that was not transferred, I have to subtract it from this IC. So in the case of where you have leakage current, okay, so in alpha, my DC transfer ratio, I have to subtract that. That's gonna be IC mod subtracted minus ICB. All right, so call this equation 2. All right, so I hope that is well understood. Okay, so please take note of this equation 1 and equation 2. Now we're still going to express more, okay, we are still going to derive more formula. Of course, in transistor there's a whole lot of formula, right? But at the end of the day, I will summarize the formula and actually list out the important ones, the one that will help us solve typically uh, questions. Okay, now let's look at, we already know, okay, that in a transistor the emitter current is equal to the base current plus the collector current. We know this already. Okay, so if we already know this, that simply means that now I have to do some substitution, right? Knowing quite well that collector current is equal to alpha IE plus ICBO. So I have to do the substitution. Okay, let me substitute. So invariably now I'm gonna have I IE is going to be equal to IB, then plus IC already is alpha E plus ICBO. Okay. Plus ICBO. So I want to rearrange this equation now. I wish to rearrange the equation. Okay. So what do I do? Okay, or better still. Okay, please pardon me. Let me make it very simple. Okay. Okay, since we already know that IC is equal to alpha E plus ICBO, all right? So invariably now, from this particular expression, I will have alpha E equal to IC minus ICBO. IC minus ICBO. So now, if I now make IE the solution formula, IE is going to be equal to IC minus ICBO, then divided by alpha. Okay, so let's flow. So let's now put that into this particular formula. All right. Let's put that into this formula. So at this point where I have IE, all right, I'm having that's gonna be IC minus ICBO divided by alpha plus, oh please pardon me, equal to RB plus IC. Okay, so cross multiplying. If I cross multiply, I'm gonna have IC minus ICBO equal to, that's gonna be alpha IB, okay? Then alpha IC. Okay, so rearranging this equation, I'm making IC the subject. I'll take alpha IC to the other side. I'm gonna have IC minus alpha IC minus alpha IC is equal to alpha IB. Okay, then plus ICBO. Okay, so let's see flow. So I want to factorize. Because I want to make IC the subject. So of course, factorizing IC, I'm gonna have IC bracket open 1 minus alpha, okay, equal to alpha IB plus ICBO. So that simply means that my IC now, collector current now, is going to be equal to alpha IB plus ICBO, then all divided by 1 minus alpha. Okay, so you can decide to separate the fraction. You can separate the fraction. So you can separate the fraction or you can leave it that way. But let's I think it should be ideal for us to separate the fraction, okay? So that we separate the leakage from the majority carriers. So I'm gonna have alpha I B all over after alpha I B all over 1 minus alpha, then plus ICBO divided by 1 minus alpha. So that is my collector current. Okay. So this relationship between my collector current, okay, and the leakage current of an open emitter, okay, in collector in a base configuration of the circuits that we have already seen up there. Okay, so just take this down as a formula. Then we are going to be looking at how, okay, we're going to express leakage current in a common emitter configuration, and that will be in the next video. All right, see you in the next video. Thank you very much.